Hey everyone, welcome back. I am absolutely thrilled to have you here for another explainer. Today, we're taking those incredibly dense textbook engineering concepts and, transforming them into a highly practical toolkit you can actually use. We're focusing squarely on part two, material selection and standardization. Honestly, if you've ever wondered how engineers can look at a massive list of metals and know exactly which one will keep a machine from literally tearing itself apart, well, you are in exactly the right place. Let's get into it.
Okay, let's dive into this. Here is our roadmap for mastering material science today. We'll hit core mechanical properties first, then move on to stress, strain, and limits. After that, we'll look at material selection criteria, followed by standardization and BIS codes. Finally, we'll wrap the whole thing up with some high-yield exam pointers.
All right, section one, core mechanical properties, the alphabet of engineering. First up in our rapid-fire definitions, we've got hardness. Now, a lot of people tend to confuse hardness with general strength, but it's actually much more specific than that. Hardness is really about a material's ability to survive wear, scratching, and permanent indentation over its entire lifespan. Think of it as the shield that keeps a machine part from degrading when it's constantly rubbing against another part. And we don't just guess here. Engineers determine hardness using very specific standardized methods. You'll hear about the Brunel, Rockwell, or Vickers hardness tests. Next, we have creep. Now, creep is kind of like a silent, slow-moving threat to materials. Unlike a sudden, catastrophic break, creep is this progressive, permanent deformation. It happens over a long period of time when a material is under constant stress. And it is especially dangerous at high temperatures. Imagine a metal component tucked inside a steam plant or a jet engine. Over thousands of hours of intense heat and constant load, that metal can actually slowly stretch and distort. That right there, that's creep in action.
Now, what's really interesting about this slide is the extreme contrast in how different materials fail. On one hand, we have ductility. This is the extent to which a material can sustain plastic deformation before it finally ruptures. Basically, how far can you pull it? And here's a fun fact for you. Gold is actually the ultimate champion of ductility among metals. But on the exact opposite end of the spectrum, you've got brittleness. A brittle material undergoes almost zero plastic deformation. It just suddenly snaps or shatters without any warning. We also need to draw a really strict line between two terms that sound similar but dictate entirely different manufacturing operations: ductility and malleability. As we just noted, ductility is about a material being drawn out, like stretching it into a long wire without rupturing. Malleability, on the other hand, is a material's ability to be hammered or compressed and flattened into incredibly thin sheets without cracking. Distinguishing between pulling a material and flattening a material is absolutely crucial when you're deciding how to forge or shape a specific machine part. Moving right along to Section 2, stress, strain, and limits. This is where we start pushing materials to see how they handle real-world physics. Let's break down the visual math of stress. Stress, which we denote with the Greek letter sigma, is simply the applied force divided by the cross-sectional area. Conceptually, you can think of stress as the internal resistance offered by a part to an externally applied force. So when you pull on a metal rod, the material fights back. That internal fight spread evenly across the area of the rod is what we call stress. And so, what happens as a result of all that stress? Well, strain. When a uniaxially loaded rod stretches, that physical deformation is strain, represented by epsilon. It is exactly the change in length divided by the original length. It's essentially the visible, measurable consequence of the stress we were just calculating. Now, you might be wondering, how far can we push it? Well, every material has an ultimate stress point, the absolute maximum load it can take before it just completely breaks. But in real-world machine part design, we don't go anywhere near that. Instead, we use what's called working stress. This is a deliberate, life-saving engineering decision. We purposely maintain a safe stress level that is significantly lower than the ultimate breaking point. It's basically the everyday load the part is designed to handle comfortably. So the crucial point is that the gap between that safe working stress and the ultimate breaking stress is determined by the factor of safety. The factor of safety is essentially the engineer's ultimate safety net. It protects against unpredictable failure, unexpected overloads, or even tiny unseen flaws in the material. Honestly, it is the exact mathematical buffer that separates a brilliant, enduring design from a catastrophic failure. All right, on to Section 3, material selection criteria.
Let's see how these theories guide us in matching parts to their true purpose. And this brilliantly illustrates how we actually map out different steel specifications for entirely different jobs. Check this out. For furnace doors or heavy-duty gears, you need something incredibly robust, right? So engineers select nodular cast iron, specifically SG 800-2. But if you're making gear shafts, axles, or pinions, you shift gears to plain carbon steel, designated as 60C4. And for highly stressed dynamic parts, things like crankshafts and connecting rods, you absolutely need low alloy steel like 35Mn2MO28. It's amazing how different jobs require entirely different microstructures. But selecting a material isn't just about blindly reading a chart of strength values. Design is fundamentally a complex decision-making process. It's a huge balancing act. You have to carefully weigh the specific purpose of the part, the physical size of the end user, like is this for an adult or a child, alongside strict material strength requirements, the cost, and even the final aesthetics. That brings us to Section 4, Standardization and BIS codes. These are the strict rules of the road that keep the global engineering community on the exact same page. So, according to the Bureau of Indian Standards, or BIS, there is a very specific methodology for designating steels. As you can see, they mandate that a minimum number of symbols must be used to designate any given steel. This is a real game changer because it ensures that a material specification is never just left up to interpretation. It is precise, standardized, and legally defined. Just to quickly clarify how this works, there are two primary parts to this standard that you definitely need to remember. IS 1962 Part 1 uses letter symbols to classify steel, whereas Part 2 uses numerals. Knowing this subtle difference between the letter-based and numeral-based designations ensures you will never get confused or misread a material spec sheet when you're out there on the shop floor. Let's move to and see how this builds into our final segment. Section 5, High-Yield Exam Pointers. Time to ace the test. Okay, get your notes ready. Here is a high-energy, rapid-fire rundown of the most heavily tested 2-mark revision questions from our source material. You absolutely must be able to concisely define the factor of safety. You need to clearly differentiate between working, yield, and ultimate stress. And definitely expect comparison questions like what is the difference between ductility and brittleness, or what separates hardness from toughness. Memorize these definitions exactly as we covered them today for sure. Now, for the heavy-hitting 5 and 10 mark essay questions. This is where you want to dedicate some serious study time for maximum marks. Be prepared to list and describe at least 10 mechanical properties in detail. Crucially, you must be able to sketch out the stress-strain curves for mild steel and cast iron. And please, make sure your axes and yield points are perfectly labeled. Finally, be ready to write out the general step-by-step procedure of machine design. Wow, we've covered a lot of ground today, haven't we? From the basic alphabet of properties to the strict codes that govern them all. I want to leave you with a final, slightly provocative thought to take beyond your exams. If design is essentially a decision-making process, balancing risks, forces, and real-world limits, what factor of safety will you build into your next great idea? Keep learning, keep designing, and I'll see you in the next explainer.